Yes, yes. Okay. Okay, guys. So thank you for coming this workshop. And my name is Ma. I'm a PhD student at Professor Feng Yanxia's group at Yale. And this afternoon we are going to have 4 speakers. The first speaker is Dr. Keji Lai at University of Texas at Austin. So let's welcome Dr. Keji Lai, and you may start, Dr. Lai.
Okay, wonderful. Yeah, thank you for the introduction. And so first, let me thank Bing, Fan, and all the organizers for putting together this wonderful workshop. I have certainly learned a lot of knowledge in the past 2 days, and I look forward to learning more. So a couple of months ago, when Fan was organizing this workshop, he asked me to give a talk. And I said, well, I did very little. It's basically, I can give, a talk in 2 minutes, definitely not a 45 minutes sort of workshop talk. And he said, that's okay. Just tell us about your technique. I said, okay, sure, I can do that. But I would like to ask the audience to lower your expectation, lower it to, I don't know, negative infinity, such that you won't be too disappointed in the next 30, 40 minutes. So I have reasons why I have been sort of a little bit reserved on the results we have taken so far. And I'll tell you about those. So I'm going to give a slightly unusual talk in that most of the time I sort of advocate for the advantage, let's say for the pros of the technique. And for this talk, since it's a lively discussion with a lot of graduate students, I'll tell you a lot of the negative or the cons of the technique, which we are definitely try to mitigate. Okay, so let me get started. And so I would like you to meet with my group, which is a group of highly motivated and talented people. And the reason I can't give a good talk today is not because of them, it's because of me, who is mostly holding a lot of the project, holding this particular project back. But I think I'm pretty much convinced by Fan and also convinced by a lot of the work that you guys have done, a lot of the results we have seen in the past 2 days. And so I promise we will go full speed on it after this workshop, right? So here are the funding agencies that are supporting a lot of the works that sort of going on in my group. Okay, so let me get started. So this will be mostly sort of introduction of the kind of the technique in my group, and I'll try to make it as close to the Quasi-1D sort of imaging as possible. So so this is the outline of my talk. I'm going to sort of first introduce the technique, again, both the pros and cons, and I'll show you how we use this technique to measure both the trivial and topological conductive edge channels. And I'm going to show with maybe just one slide of really preliminary results on the bismuth bromide and bismuth iodine data, which is again very much preliminary, and I'll summarize after that. So the type of experiment or the type of physics that we try to sort of perform is, we're trying to get a spatial resolution which is million times smaller than the wavelengths in the free space of electromagnetic waves. So in other words, we are sending electromagnetic waves through some type of waveguide transmission line to a sharp tip with the dimension of the tip of about 10 to 100 nanometers. And since this dimension right here is million times more than the wavelengths, you don't really talk about wave at this point. It's really just a quasi-static, just a time-dependent type of measurements. So any change of the sort of the impedance seen by the tip, which again we can just use lumped elements as capacitance and conductance, and this will be detected by microwave electronics. So a capacitance will show up in the imaginary part of impedance. Well, it's actually the inverse. It's actually the admittance, but we mostly just talk about impedance. And vice versa, the real part, which is the lossy part, will occur at the real component of the microwave output. So pretty much anything that coupled the tip to the sample. So permittivity, dielectric loss. So permittivity is essentially when you swing the electric field, you get the material to be polarized. And the dielectric loss is mostly related to dipoles. When the dipole frequency is comparable to the frequency of the electric field, then you have loss. And of course, everybody knows the ohmic conductance, which again appear as a conductance in the impedance. And last but not least, one can also have piezoelectric coupling, which is appearing again as a loss mechanism to the tip, which convert or transduce the electric field to sort of mechanical energy, electrical energy to mechanical energy. And with this type of measurement, we can get extremely near field resolution, which is again comparable to the tip apex. And so here's essentially the contrast mechanism I just mentioned. It could be dielectric. If it's a purely imaginary part, we will get permittivity contrast. And once we see some real part, then we know it's one of the three: dielectric, conduction, or piezoelectric transduction. So so that was pretty much a conceptual drawing. So this will be a more like a circuit type of drawing. And again, this is, so for those of you who are not expert in microwave technology, you can pretty much just ignore it and just trust us. We can get sort of frequency around several decades from around 10 megahertz to 20 gigahertz. Spatial resolution mostly determined by the tip diameter. And the sensitivity, it's around attofarad in terms of capacitance. And the pros of this technique is that the measurement is completely non-invasive. So we don't really need to put any electrodes, don't need to make any devices on the sample. And we directly read out this information with some prior knowledge of the sample. And we can also do subsurface imaging, which is because the coupling is dielectric, so we can easily see through a, let's say, 20, 30, even 100 nanometers of dielectric. Right? So both of these are fairly unique, I would say, which allows us to measure quite a bit of materials that I will sort of introduce later. Now, before I move on, I would like to just tell you that, let's say if we have a material, let's say you have a 2D layer underneath a dielectric layer. So this is a quasi-static simulation of how the field is distributing. So one can easily understand this. Let's say if the material is very insulating, so the electric field, so this is the potential. So, you can just do the derivative or gradient in your mind, and you can see this is electric field. Right? So electric field going this way, so electric field easily going through an insulating layer. But electric field will stop at the conductive layer because the electrons will screen the electric field, so that the electric field is very much concentrated underneath the tip if the material is very conductive. The 2D material is very conductive here. So roughly speaking, the two channels will show something like this. So this one is proportional to capacitance. So as the material getting more and more conductive, the capacitance. So this is a small capacitance, and this is a large capacitance. So the imaginary part goes up monotonically, and then there is a lossy region, somewhere in between. And then after this, the loss goes downward. And this is about, so you do the inverse of this. This is about a mega ohm per square, right? So for those of you who are doing transport, you know a mega ohm per square is very insulating for a lot of the quantum system, right? Because quantum resistance is 25.8 kilo ohm per square. So in other words, we are fairly sensitive in the insulating part, but once the material gets a little bit conductive, we start to lose the sensitivity. And this is one of the reasons that I'll tell you later. One of the reasons that I feel a little bit puzzled by the data we took. Okay, so let me, again, for experimentalists, you might want to see how this thing is actually performing, right? So we have tips, we have two type of cantilever, two type of microwave tips. One is cantilever, and the other one is built on tuning forks. And over the years, I have a number of systems set up in my group, which we can cover a very wide range of temperature, going from room temperature all the way down to about 100 millikelvin in a dilution refrigerator. And we have optical access, laser path, and also a system which, two systems which allow us to access high magnetic field. Okay. So let me quickly show you a number of MIM, microwave impedance microscopy results on different type of mechanism. So this one is on permittivity. So the material is bismuth, selenium, oxygen 5. It's a fairly good high K dielectric. And by just imaging this, we can directly read out. Of course, we did some simulation of the permittivity, but no need to do any patterning, no need to do parallel plate capacitor, and we can directly measure the permittivity as a function of thickness. And so this is a 2020 work. Actually, we published another one again on Nature Electronics right this year. Actually 2022 is already last year, and went all the way down to like 2 or 3 nanometers. And so this result shows the dielectric loss. So the material is called yttrium manganese oxide, and it's a ferroelectric material. And as you can see in the loss channel, you see the domain walls. So this is piezo force microscopy, which you see the up and down domains. And in the domain walls, it turns out the domain walls are very lossy. They are very insulating at DC, but they start to become fairly conductive at a few gigahertz. And so this is the work we've done for imaging dielectric loss. And like I would say 80% of my work is on conductivity. So this particular work shows a imaging of this complex oxide through just like 2 degrees Kelvin. And there's a phase transition within this around 114 degrees Kelvin. And you see during the phase transition, there's this stripe phase, which are much more conductive than the background during the phase transition. And the last one was actually, again, a surprise to us. We figured out that we can actually image piezoelectric transduction on piezoelectric materials. This is ferroelectric material, but it's also piezoelectric. So here you see the nice sort of interference patterns of acoustic waves that's sort of generated on the sample surface. Okay. So for today, I'm not going to go into detail of any of these, but I would try to sort of adapt to the topic of this workshop, which is 1D channel, conductive edge channels. Okay, so let me start from the trivial conductive edge channels on a transition metal dichalcogenide material. So this is MOS2. I'm sure that many of you already know a great lot about this material. So I won't speak too much about the So this is the device configuration. So it's a very straightforward backgated MOS structure. So it's a backgated metal, oxide, and semiconductor, and we're measuring from the top. So the material is a fairly okay. So this is a MOS2 flake exfoliated from the bulk. On one side is about 3 monolayer, and the other side is about 4 monolayer. And if you do the transport, you can measure the mobility is about 10. So it's a decent but not a great material. So let me show you the result. So this is again, just a guidance of what you would expect. So as we turn on the backgate voltage, we're gonna essentially increase the bulk sheet conductance. And during this process, we should expect that the real part, the imaginary part, which is the capacitance, increases monotonically, and the resistance or the loss part increases up to a peak and then drops back down. So this is essentially just how the electric fields distribute between the tip and the MOS2. So I have some movies about, so let me wait a little bit. So let's start from very negative. So you see everything is insulating, and gradually as we turn on the gate, this part gets conductive and this part gets conductive later. Right? And the imaginary part monotonically becoming brighter and brighter. The real part, let's wait a little bit. The real part, which is lossy part, gets bright. And at some point, it starts to dim and then it disappears at a very high gate voltage. Right? So if you just plot the overall signal as a function of backgate voltage, they track the simulation curve fairly well. So I would say at least this tells us the picture is correct. Now, I'm sure you guys can tell at the very edge of the sample, there are conductive lines that appear before the bulk gets populated. So this one's up. So we can just get a line cut through the edge, and then we track this edge and we plot the signal as a function of position. So at very negative part, you see there's actually a dip. So this is a very typical topographic artifact, and I'll talk about it later. But so you see a very small signal, and you see this double feature. But very soon you start to see something that's definitely not topographic related. You see the peak here, and the peak actually increases, and eventually the edge channel sort of merge with the bulk. And we can actually do simulation of the signal and then sort of calculating the effective signals at the bulk. The effective conductance at the bulk and the effective conductance at the edge. And note that this is not infinitely high. So this means this is the edge. The edge is still lossy. The edge is still lossy. Okay, so so this is like a 2 monolayer, or 3 monolayer, 4 monolayer. You might ask, what happened for a monolayer, single layer? And the result is pretty much the same. So the imaginary part increases monotonically, real part increases and decreases. And before that, you get some kind of conductance near the edge. Right? So, the physics, I would guess you guys already know what's happening. It's just some dangling bonds, especially in one particular, I forgot, it's armchair or if one calculates the in-gap states, you'll see at the edge, this dangling bonds is contributing some kind of in-gap states. So when you use a gate to move the Fermi level up, so at some point it's going to first hit this in-gap states. So in the real space, they locate at the edge of the sample. So that's why you see it. And so people know about it, and it's of course it's a nice way to sort of really demonstrate that they do exist. And in addition to use a gate, we actually also use sort of photoconductivity. So this is another paper, sort of follow-up one, that we use a laser to shine, or actually many different wavelengths, diode lasers, to shine from the bottom, and we measure from the top. And again, there's no need to put any contacts. The image itself is telling us which part become conductive first, which one become conductive later. So this is a monolayer, bilayer sample. In the dark, you don't see anything. And as you continue, as you shine it with a below gap laser, you see the monolayer and bilayer are still insulating, but the edge start to show up, the bilayer edge. And then you increase this, you start to see that the monolayer edge also start to become bright. And if you go to this paper, you will see we went all the way to very high photon energy, and then everything. Please, yeah.
Here,
yes.
Any particular reason bilayer edge shows up first, and then the monolayer edge?
Right. Yeah, thanks for the question. Yeah, so right. So in the paper, we also had some, I believe it's a postdoc in Alan McDonald's group helping us to just calculating this in-gap states, where they are. And so first of all, the bilayer has a smaller band gap compared with the monolayer. And then the position of those in-gap states are also lower in terms of their energy. So that's why as we shine laser, those are the region that gets bright first.
So that means the tri-layer could possibly have even.
I believe so. Yeah,
okay.
I believe so. Yeah, I believe so. Yeah. Okay, so let's.
May I have a question before you go to that part? And so by experiment alone, why do you think the edge state is trivial?
Yeah, very good question. Yeah, so I'm going to show you immediately how do we compare. But since you ask, so trivial means you can kill it, right? So basically, like if you go backwards, right? If you go backwards and you see you go from very conductive and going this way, and it's gone here. And so same thing here. It's gone when you sort of go to the very negative part. And for the topological one, the bulk will be depleted, but the edge will always be there. I'll show you right away.
I see. So basically, you're thinking of because the edge conduct channel do not exist all in
right.
anywhere in the gap.
Correct.
Okay.
Yeah.
I
so
see.
you pull this one down.
I see. Yeah. In fact, I have to point out one thing is that the conductive edge state you observe here, they are trivialized the edge states, but however, the origin of them are actually topological. The origin is because there is a so-called a quantum valley Hall phase in monolayer. In bulk there is a kind of valley projected topology there, but at the boundary because of the symmetry breaking of the two valleys and many other things becomes trivialized.
Right. Yeah, no, I totally agree with you. Yeah, so I believe about a decade ago there's quite a few theoretical work on this. And I think it's as you said, it's pretty clear now. There's a lot of sort of things that are sort of coming together to make this edge trivialize.
Yeah, just a side comment. There is a field. They working on the so-called mirror, a twin mirror boundary.
That's right.
In TMD system, and right. They also observe actually a larger liquid behavior, and
that's right.
The no-load works, right? And I think it's similar to what you observe here, just different physics, but the same states.
That's right. Yeah, wonderful. Okay, so I guess I'll probably go a little bit faster. I do want to share with you the the preliminary results, and here you are thoughts. So let me go quickly through this. These are also some prior work. So again, I don't think I need to sort of go through this in detail. So there are a lot of quantum Hall related states with so non-trivial either Chern number or Z2 number, and so the bulk of these systems are either in Landau gap or just a bulk gap, but the edges are conductive, because they because of topology. So there's this either the Landau states or the edge state that cut through the Fermi level. So transport-wise, you see this nice oscillations in quantum Hall effects, and you see the quantization of conductance or the Hall resistance in quantum spin Hall and quantum anomalous Hall states. And theoretical pictures, of course, is always this topologically protected edge channels. And it would be always nice if we can have spatially resolved information for these systems. So when I was a postdoc, I did this quantum Hall sort of measurements on very traditional gallium arsenide 2-deck. And so I'm going to very quickly show you. So this is more than a decade ago. So we essentially patterned this into small dots. And so we measure different dots at the different magnetic field for unfortunately those dots, if we don't do that, somehow this very shallow 2-deck is getting depleted. So you're going to see a lot of these images, but they're taken from so we patterned the sample into many dots, and these are from different ones. So we start from here, very far away from the quantum Hall dip. And then we gradually enter this dip. And I'm sure everybody can start to see there's a sort of a ring that's higher signal, and a ring here, which is lossy. And then this feature gets stronger and stronger. And the material becomes very lossy in the middle of the quantum Hall system. And then again, eventually it goes up and then it disappears. Right? So I need to say that if you convert this, so this is in kilo ohm scale. If you convert it to ohm scale, this does not go to 0. So this temperature is not low enough for us to see completely 0. So hopefully that explains this. And so the physics is fairly straightforward. You have this density profile that cuts through the localized states. And at filling 2, you have a lot of the lossy states in the middle. And as the filling factor gets smaller and smaller, eventually the material becomes conductive again. And we can actually quantify the size of the metallic strip and the insulating strip from our images and plot them as a function of filling factor and compare it with the theory. So again, if you're interested, this mostly in this PRL paper quite a while ago. So then we move on to look into quantum spin Hall system in mercury telluride and cadmium telluride system. Again, this was a hot topic more than a decade ago, but some of you may not be that familiar. So let me just say one or two sort of sentences about it. So cadmium telluride, the band structure is the so-called normal structure. So you have S orbitals above the p orbital, and because of the strong spin orbit coupling in mercury telluride, then in the bulk, the p type sort of band is actually above the S type band. So, but of course, once you put them into the into a quantum well, then because of the finite size effects, you might have this part getting inverted back again. So there is a critical point below which the mercury telluride is normal, and beyond which it's actually inverted. So this one shows the normal one. And so in the quantum well, the electron band is above the hole-like band. And when in a relatively wide one, then the electron-like band is below the hole-like band. So then you have the quantum spin Hall edge states. So this is, again, a simple theoretical picture. And the experiment was done, again, back not here at Austin, but was at Stanford in my former postdoc lab. So this is a tuning fork on top of mercury telluride. And so for the trivial states, you see here, so again, to answer Fan's question for the trivial one, so this is just a line scan. Right? So by changing the gate voltage, you see here is the whole, this is the hole-like states, and this is the electron-like states. And but in the middle, you can completely kill the edge states. Whereas in the topological one, the edges are always conductive. There we go. So that's sort of an evidence of the topological features. So let me quickly share with you some very recent data we took on quantum anomalous Hall effects. So the sample was from Ken Wang's group at UCLA. So this is a MBE grown bismuth antimony beryllium system on mica. And it's double doped on the top and the bottom. So the top is doped with vanadium with a coercive field around 250 millitesla. And the bottom one is doped with chromium with a HC of about 0.1 Tesla. And so the magnetic dopant essentially opens up a gap in this topological insulator. And so there's, again, an edge states that goes through this. So we did transport in our fridge, which has a base temperature around 100 millikelvin. And so if you trace this going from high field, let's say 2 Tesla, and you see this drop, the first drop corresponds in the Hall conductance corresponds to a peak in the sigma XX. So this is sort of where the chromium flips. And then there is a plateau at the 0 sigma XY. And then there's another drop, which corresponds to the flip of vanadium. Okay? And things will come back again. Now, this is unfortunately not a best sample. As you can see, this, again, I'm using this unit, but if you blow this up, it's not at 0 yet. Okay, so we do simultaneous transport and imaging, the microwave imaging. So this is the imaging results. So let me show you what this means. So this is a line image. Right? This is a line image. And during this line scan, we change magnetic field. So from 2 Tesla to -2 Tesla. And at 2 Tesla, you see the nice edge state. So this is the sample, and this is the substrate. This is mica, and this is the quantum anomalous. So sorry for the title. This should be the bismuth telluride. And around this magnetic field, you see the entire sample become conductive, and then there's a region when the edge disappears. And then there's a region where, again, the entire sample become conductive, and then it flipped to the C equals to -1 quantum anomalous Hall. And if we trace the center, we see similar features as the transport. So this one is the flip of chromium, and this one is the flip of vanadium. Okay, and if you go here, if you take a real image, like a spatially resolved image, you see the edge states, and then in the imaginary part, and then the real part. So we're still trying to understand why the edge appears so broad. This is almost a micron, and our resolution should be much better than this. It should be like maybe 100 or 200 nanometer. But it's not just us. I believe some earlier work coming out from Stanford also show very broad edge states, even though theory tells us this should be just atomically sharp, maybe a couple of unit cells. Okay, so from this one we can actually simulate, and so this is the distribution of the conductivity, and beyond this it should just go to something that's our signal saturates. Okay, so I guess I probably have just a couple of minutes left, and I do that on purpose so that I will definitely share with you some results, but we don't have any conclusive analysis yet. Okay, so again, thanks to Professor Takeshi Kondo for sending his student to my group. That was way before the pandemic, so quite a while ago. And you have heard many excellent talks about this material, bismuth halogenides. So I'm not going to spend much time on this. So especially in Professor Kondo's talk, you hear that so by doing different type of stacking, you can have different phases of bismuth bromide or bismuth iodine. And so there was some sort of pleasant and nice debates about what the nature of alpha bismuth iodine is. But at least at that time, our work is mostly on the bismuth bromide. I'll show you something here as well. So the result was sort of done, I believe, in 2019, and so I just had a lot of trouble in understanding and sort of believing the results until I would say probably after seeing the nice result coming from Princeton's group, I feel much better now. But at that time, let me show you. So this is one of the results. If you were listening to Professor Kondo's talk, you probably already saw this result. Okay. So this is an exfoliated bismuth bromide. And at that time, the exfoliation somehow only gave us, a very thin, a very narrow ribbons if we want to get to like sub 50 nanometer sort of height. So and we work with this, and so at room temperature we did observe some fairly strong hints of this edge states. So let me show. So this is a line cut through an AFM, which shows up here. And this is a line cut of this MIM. I believe this is imaginary part. And this side, you clearly see this double feature. So this one we know very well. So this is when the tip approach here, it sees more material. And when the tip climb up a step, it sees less material. So when we see this, we say, okay, this is not real. So this is just topographic artifact. But on the other edge, you see fairly nice bright lines. Or if you don't trust me here, you can look at this one. So here you don't see this double feature anymore. It's just a bright line. It's a bright line. And we see this type of results again and again. And so there's one result here. So you see this is a bright line, and a bright line on this side and dark line. So this is part, this is really just artifacts. And this appear again and again, double features on this side, and then bright ones on this side. So why do I say I'm not convinced? So if you recall the examples I gave you earlier, the quantum Hall effect was taken at 2 Kelvin. The quantum spin Hall effect was taken at 4.5 Kelvin. And then the quantum anomalous Hall was taken at 100 millikelvin. Right? So as a quantum transport person, I guess it's just me. I usually think, okay, we need to cool down these things to at least 10 Kelvin or maybe 4 Kelvin to show it's topological. Unfortunately, at that time, our low temperature setup had a lot of problems, And the magnetic field data, we did go to about a couple of Tesla. And we just can't repeat things. Sometimes we see something, sometimes they don't appear. And so just on the conservative side, I say, okay, why don't we put these results in the supplementary data? And then after that, immediately the pandemic hits, and I sort of dropped the ball until Fan sort of convinced me. And also after I saw the nice result from Hossain's group showing that even at room temperature, you could expect things coming out from this material. So just this past Thanksgiving, we had very fortunately that Fan connected my group with Bing's group at the UT Dallas. And this time we get samples much wider. So if you pay attention, these ones are like a micron in width. We can get wider, but it's not that large. But with from UT Dallas, those samples are huge, like very large dimensions. So here I just show a number of results on the bismuth bromide. Right? So you see the common feature is this is huge. So let me come back here. These are all volts. Volts to us are very large. And same thing here. So this side is the atomic force microscopy. This side is the microwave image. And I would say we pretty much see, at least we see similar things. Right? So you see that volts, large of signals, and very large signals on some edges, not all of the edges, some edges. And some, but some other ones are like this one is clearly just topographic artifacts. If you see the bipolar, it's huge. The signals are just really large here. And interestingly, right, so Bing also gave us some iodine sample. So for iodine sample, if you compare, so you compare the scale, this is hundreds of millivolts, and sometimes even this is for those of you who used to look at this this force color scale, they're only about here. So for the iodine samples, the signals are much weaker, and we never see volts like bright lines. Okay? And so I must say this is really preliminary. So we got a sample around Thanksgiving, and these were taken during the winter break, and we didn't even have time to fully analyze them. But after listening to many great talks in the past 2 days, I think at least this is telling us something. It's telling us that maybe this indeed is quite different. So most likely, this, for example, this is maybe in the alpha phase, and but we need to heat it up and see whether we can access the slightly higher temperature and sort of getting these bright lines in the iodine sample. So there are many things we're planning to do. So first of all, these were taken at room temperature, ambient, and we already observe, even we just scan this, let's say 24 hours, the signal gradually decrease. So the material, these edges, this freshly exposed edges, definitely is aging under the usual atmosphere. So we will do it in vacuum pretty soon. Right, so that's the first step. The second step is we want to do a systematic step height dependence to like zooming into this small steps and see whether we see any dependence of the signal strength as a function of the height. And we also hear that even for the same height, the left edge and the right edge could be different. Right? Again, from Shafayat's nice talk yesterday. And after this, we will do some quantitative analysis and see if this large signal makes sense. And after that, we're going to cool the sample down and use magnetic fields to really find out whether they are topological or not. Okay, so with that, let me summarize. So I hope I have doing a reasonable work on introducing the technique. for imaging the local permittivity and conductivity. And then I showed the imaging of a trivial conductive edge and then the topological edge, and very preliminary results. And I'm looking forward to working with Bing and Fan and many of you, trying to understand this very interesting material system. So with that, let me end here and see if I get any questions.
Maybe I can have a quick question here.
Sure,
I think
yeah.
the data is really nice, and let's see, just on that slide. So, what is the temperature of your measurement?
Yeah, these are all room temperature ambient. So we just exfoliate and measure immediately, and we do see some time. Yeah.
Your bismuth are just right at the boundary of phase transition.
Yeah, that's right. Yeah, you are exactly right. Yeah, so it's a fairly easy experiment that we just heat up to like I don't know 40 degrees Celsius. We should be then it's a direct test, whether we recover this this bright lines, in the iodine sample.
So can I have one question?
Go ahead. Yeah. Yes.
Yeah. Well, nice talk, Keji.
Thanks.
Are they both in the bulk? Are they both insulating sample or metallic sample for the two material?
Yeah. That's an excellent question. So first of all, if we use the criteria of the temperature dependence, right? So this they all go up. So the bulk, they're all insulator. But if you look at the numbers, so these are done at 300 Kelvin. So these are done at room temperature. So they are all like 0.1 on that order. I would say 0.01 to 0.1. Different sample probably have different bulk sort of doping. Ohm centimeter. So that's it depends who we're talking to. If you're talking to a metal, scientist studying metal, they will tell you, ohm centimeter. Milli-ohm centimeter is already large for them. But for people doing semiconductor, this is not that large, right? So I would say they're pretty reasonable semiconductors at room temperature.
Thank you.
Yeah.
And Keji, I can add it up. I believe
Sure.
on the bismuth iodine, the one we show on the PRX paper is the most insulating at this stage among all the published data.
Right.
That's basically that's why I was convinced at that time our sample is really of high quality. Right. Because really compared to all the existing ones. But that's the one you probably something you can look into. That's basically the skill of how insulate, how can we call it metallic or insulating.
Right.
Yeah, I'm very excited to see this as well. Yeah, this is actually pretty good. So that means the bulk doping is very low. Yeah.
I can see Dr. Jenny Law is raising her hand. So.
Oh, okay, sure, please.
Oh, yeah.
Please.
Yeah, thanks. Yeah, that's really interesting data. So I just actually want to clarify a bismuth iodine. Which phase? Maybe I missed it. Which phase do you think it is?
Right. So I initially put it here, but I remove it because I see the sort of the nice debate yesterday between different groups. I think Bing will probably tell us this is the alpha phase, and I kind of agree, but I would definitely the next the immediate experiment will be just to heat it up. Just as Bing said, we are right at the phase boundary. So yeah.
Sorry.
Yeah,
so even in the alpha phase, shouldn't you also have some hinge states or edge states?
Well, see, that's so again, depending on who you ask or who you talk to, right? Right. So I think the theory, we'll probably ask Fan, yes, in that case, but these are the data we took, and it's systematic. So it's not just here I pick, of course, just two pairs of data, but we systematically, so bismuth bromide, we usually see, the scale bars are usually several volts to show them, but the iodine, it's 100 millivolts. So these are coming from 10, 20 images. They're fairly systematic. So they may tell us something, but I will don't hold me accountable for that yet. So it could be that, I don't know, maybe this one ages fast. We see aging. Yeah, we definitely see aging.
Yeah. This is done at outside, or this is inside the cryostat?
It's outside. It's outside. It's ambient. Okay. Yeah, it's ambient.
Yeah, I do think iodine seems to be fairly sensitive.
Sensitive to air, right? Yeah. So the next step is just exfoliate immediately pump down. Yeah. And then we'll compare.
Look forward to the data.
Thank you. Yeah, thank you.
So Keji, there is one point here. The bismuth iodide, the side surface has a much smaller gap compared to the bismuth bromide. So what that might affect the observation here, but I'm not sure. I'm just pointing out some fact.
At the end of the day, it's
even the hinge states are different, right?
Hinge states are different.
Yeah, the profiles are different, but somehow, the most important thing here is that they do exist, but the surface gap is smaller for bismuth iodide. I mean, on the side surface. So the other thing is for both materials, if I understand correctly, you didn't tune the Fermi energy. So
no, that's right.
So why the Fermi energy has to be in the gap of the bulk?
Yeah. So let me do more. Let my students do more. I think they are in the audience, so they hear all the questions.
Do we have any other questions for Dr. Lai? If you know, perhaps we can move forward. Next speaker, let's welcome Dr. Sanfeng Wu from Princeton University. And he's going to talk about two-dimensional Lottinger liquids in a Moiré superlattice. And